Hello everyone, and welcome to our first part on trigonometric substitution. So this is yet another integration technique that we're going to learn in Calculus 2. However, before we jump into that, I'd like to do a review problem from Calculus 1. So the review problem is integrate x times the square root of 2x squared plus 2. And if you want a hint, actually if you don't want a hint, go ahead and pause now and try the problem. But if you want a hint, try use substitution. It's the last lesson that we learn in Calculus 1 here. So try a use substitution, and I'm going to go ahead and do this problem now. So the idea is inside the radical we have a very complicated expression, so we're going to make that equal to u. We're going to substitute it out by saying, well, u is going to be 2x squared plus 2. This means that du, if you take the derivative of this, it's 4x dx. And then personally, what I like to do is because I'm trying to get rid of x dx, I will solve for it over here. So 1/4 du is x dx. So now, this x dx, we can replace that with 1/4 du. And then instead of 2x squared plus 2, I've called that u. So this is going to be u. And instead of writing radical, I'll put u to the 1/2 power. Because remember, a radical is essentially the same thing as having 1/2 power. This is much easier to integrate now. So this is just the power rule backwards. So if you add 1 to the power, you get u to the 3/2. I would flip that 3/2, and I'd get 2/3 times the 1/4 I had before plus c. Now, 2/3 and 1/4, I can cross out the 2 here, the factor of 2, and I will get 1/6. And what is u? Well, u was 2x squared plus 2. So plug that back in. And don't forget that it's to the 3/2 power here, plus c. So this right here is the integral of x times square root of 2x squared plus 2 using use substitution. So we've integrated this expression involving a radical. However, we can't always use substitution to save the day. So what if you had something like this? So you have x squared plus 16 in the radical over x to the 4th. If you think about that, even if you set the expression in the radical equal to u, its derivative is not going to appear here, and you're not going to be able to cancel that effectively. So we don't give up. We actually just learned something in Calculus 2 to deal with this. So let me introduce the idea now of trig substitution. So if you see that the integrand has one of these three forms, then it might suggest that you want to use a trig substitution to solve the problem. So the first form that you would see is if you have the square root of a squared plus b squared x squared. So a squared and b squared, they're just some constants that could appear. If you had the square root of a squared plus b squared x squared, the substitution you would want to make here is x equals a over b tangent. And the way I tell students to remember this one is there's a plus sign here, and tangent starts with the letter t. So that looks like a plus sign. And it's actually the only one of these that you're going to learn that has a plus sign. So that's how I remember that one. The second one is if you see a squared minus b squared x squared. The substitution that you'd like to make here is a over b times sine theta. And then finally, the last case that you want to write down is that what if it's switched? It's b squared x squared minus a squared. Well, in this case, you're going to make the substitution x equals a over b secant theta. If you are a flashcard maker, here's 3 flashcards right here for you. Like this, you will need to know this for the exam. So go ahead and write those down and start committing those to memory. All right, well, let's see how these substitutions apply to this problem. So let's return to this this problem right here, and I'm going to show you a full, complete example of how trig substitution works. And the encouraging thing is once you've seen one of these, you've mostly seen all of them. The only thing that's tricky is the calculations along the way, but the template really never changes. So let's go ahead and look at this one. It might help in the beginning to identify what a and b are. So b squared is the number here that's going to be in front of x squared. So if you look here, I have 1 for b. So this time my b is 1. What is my a? This is the number that's off by itself here. Well, what number is being squared to get 16? Well, that's 4. And why this is helpful is because you could use this in the beginning stages if you're not sure of yourself to use the formula to get your substitution. So now I need to do x equals a over b, so 4 over 1 tangent. 4 over 1 tangent. And why did I pick tangent? Well, you have a plus here, and you're looking for a plus to use this substitution. So you're just trying to identify which of these 3 cases you're in. If this was a minus, you would have used the last one, because that's x squared minus a squared. But this one's a plus, so you'd use tangent. So that's why it's very key to memorize what you use when. OK, so now from here, I'm going to take the derivative. So just like use substitution, I have a step now where I take the derivative. Derivative of this is 4 secant squared is the derivative of tangent. So it's 4 secant squared d theta. Something else I'm going to write to help me is that x over 4, so taking this first equation, x over 4 is tangent. So I can draw a right triangle now, where if I label this angle theta, you can either use this angle or this angle. Don't use this angle, but you can use one of these. Label it theta. Tangent is opposite over adjacent. We know that from trig. So opposite is x, adjacent's 4. And if I wanted to complete the triangle, then Pythagorean theorem says that the square root of x squared plus 4 squared, that's what the hypotenuse is going to be. I'm doing that because I'm thinking ahead. I'm going to need this later in the problem. So I'm setting this up now. I encourage you to do all this in the beginning. Let's go ahead and actually apply the substitution now. So x squared, what's that? Well, x is 4 tangent. So x squared right here is 16 tangent squared. So I've plugged in x here for my substitution. This is plus 16 over. What's x to the 4th? Well, that's going to be 4 to the 4th. So I'm raising x to the 4th. 4 to the 4th tangent to the 4th. And then, don't forget this. This is commonly forgotten. What's dx? dx is 4 secant squared theta d theta. So that's our substitution so far. Immediately, I see that a 4 cancels out here and here. So now we're down to 4 to the 3rd power right here. Let's keep going. So now, notice that I have, in the radical, I could factor out this 16, because they both have a 16, and you get tangent squared plus 1 over. This is 4 to the 3rd tangent theta times secant squared theta d theta. And what you should see here is that we can make use of one of our Pythagorean identities. Tangent squared plus 1, that is secant squared. So instead of having tangent squared plus 1 inside the radical, that's secant squared. Let's continue simplifying now. So we have the integral of, I can take the square root of this now, because it's just one term in here. Square root of 16 is 4. Square root of secant squared is going to be secant. Times, I have secant squared here. Secant squared, I don't know why I wrote 3. It's secant squared. Over 4 to the 3rd power tangent to the fourth theta. Okay, so now what I'm going to do is I'm going to rewrite this a bit. So first I have 4 divided by 4 to the third is 1 over 4 to the second, but that's just 16. I have secant cubed. That's the same thing as 1 over cosine cubed, right? Secant is 1 over cosine, so I have 3 of those. Because this tangent to the fourth theta is in the denominator, I'm going to flip this up, and this is going to be cosine to the fourth over sine to the fourth. And notice 3 of these cosines now cancel out. So what I'm left with here is 1 over 16. I'll move that at the front of the integral. And I get cosine theta over sine to the fourth theta. Okay, so that looks pretty tricky. However, we can do a u substitution at this point. So over here, let's let u be sine theta, and then du can be cosine theta d theta. So we're going to make that substitution in here. So if I do that, cosine theta d theta, that's du. So I get 1 over 16. This is du over, and it's u to the fourth, which is 1 over 16 integral of u to the negative 1/4, which I can integrate that now. So this is going to be 1 over 16. I'll do the backwards power rule. I'm going to increase this power by 1. So this is negative 3. I'll divide by the new power. So this is negative 3 in the denominator, plus c. However, I need to plug back in for u. So this is 1 over, it's negative, because I had a negative 3 here, 1 over negative 48. U is sine. So I have sine to the negative 3 power. So this is going to be 1 over sine to the third power plus c. If I plug back in my sine for the substitution, however, you could rewrite this. You could say this is negative 1 over 48. 1 over sine, that's cosecant. So it's cosecant cubed. And now the very last step of the problem, you don't always need to do a u substitution, by the way, to finish this. You need to do anything you need to do from our trig integration lessons, lessons 3 and 4, anything you need to do to integrate this trig expression. You won't always have this substitution. But what you will always have at the very end of these problems is you're going to use your triangle and substitute back into the original variable. So what I need is I need cosecant. So we know cosecant is 1 over sine, and sine is opposite over hypotenuse. So that means cosecant is hypotenuse over opposite. It's the reciprocal of sine, right? So cosecant is hypotenuse over opposite. Let's look at that. Hypotenuse is this right here. So I have negative 1 over 48. And now we're plugging in what cosecant is. So cosecant is hypotenuse, which is radical x squared plus, I have 4 squared here, I'll just say it's 16, over, and it's opposite. So opposite of the angle is x. And I have to cube that because it was cosecant cubed plus c. So this right here is my complete answer. So the process can be very long. I wanted to show you a kind of challenging one to begin with. But there's this overarching template that you follow. First step is you look at the integral, you pick the correct substitution. Once you've picked the substitution, you build the picture for the triangle. Then you make the substitution, and you simplify as much as you can. You'll use your trig integration from lectures 3 and 4. And at the very end, once you've integrated, you use your picture to go back to the original variable x. Hello, everyone. Welcome back. We're going to do 2 more examples of trig substitution. Let's take a look at this first one here. So I have a good idea it is trig substitution because of the radical here, and also I have these two terms that are squares. So that is almost a giveaway. Now if I have a constant squared minus x squared, I'm going to go to the table over here. That situation is right here. I have a minus symbol, and I have a is 3, and b is 1. So in this situation, I have a is 3, and b is 1. And I'm in the second case over there. So the substitution I'm going to make is going to be x equals 3 sine theta. I'm going to take care of some of the other stuff as well for my substitution. So dx is going to be 3 cosine theta d theta. And then just so I have it ready, what I'm also going to say is that x over 3 is equal to sine theta. And remember that that's opposite over hypotenuse. All right, let's make the substitution and see if this makes this easier to work with. So if I plug in 3 sine, I get the square root of 9 minus 3 sine squared is 9 sine squared theta over, I'm going to plug in 3 sine theta here, and I'm going to get another 9 sine squared theta. dx is the same thing as 3 cosine theta d theta. So now I've completely substituted in for the theta. Now I'm going to simplify as much as I can. Recall that sine squared plus cosine squared is 1. So that's what I'm going to be using for this integral. So 1 minus sine squared is cosine squared. So if you multiply all of these by 9, it shows that this in here inside the radical is 9 cosine squared. So this is the integral of square root of 9 cosine squared theta. A 3 and a 9 will cancel, and I'll have 1/3 left out front as my constant. And I have sine squared theta and a cosine theta here, d theta. Here I'm going to take the square root of 9, which is 3. It's going to cancel with this 3 here. And then the square root of this cosine squared here, I'm going to get cosine theta times another cosine is going to be cosine squared theta d theta over sine squared theta. Now really, this is why we spent all that time on the trig integrals, is we can now integrate functions with that are just involving trig functions. So cosine over sine is actually cotangent. So what I really have here is cotangent squared d theta. And I can call on another identity that I know. So 1 plus cotangent squared theta is equal to cosecant squared theta. So 1 plus cotangent squared theta is cosecant squared theta. So if I rearrange this, cotangent squared is cosecant squared theta minus 1. And then this I actually have an antiderivative rule for. So the integral of cosecant squared is cotangent, but it's negative. Minus, and the integral of 1 is just the variable you're working with, which is theta plus c. And now I need to fill in what these two things are. So using this, I'm going to go ahead and make my triangle right down here. So theta goes here. Opposite over hypotenuse is x over 3. So opposite over hypotenuse is x over 3. And if you use the Pythagorean theorem to solve for this side here, you would get, let's call this side b. Then Pythagorean theorem says it's x squared plus b squared equals 9. And if you solved this for b, you would see that b equals 9 minus x squared under a square root. So that's what b equals. And now I'm ready to write my final answer. I can go back to the original variable, which was x. So cotangent, tangent, right, another thing that we have to remember. So everything's so intertwined. So tangent is opposite over adjacent. So cotangent would just be you flip that over. It's adjacent over opposite. So that's what I'm looking for cotangent. So cotangent is adjacent, which is b, over opposite, which is x. So that is cotangent based on my picture. The angle theta, if you solve that up here, so I know that x over 3 is sine. To cancel sine, I take sine inverse of both sides. So sine inverse of x over 3 is equal to theta. So that's what needs to go here for theta. So I get minus sine inverse x over 3, and then plus c. So now I've substituted back into my original variable. So to get theta, all you do is you solve for theta in your original substitution. OK, things look fine over here. In a moment, I'm going to begin this example. All right, so let's take a look at this one. I've done this one because this is the last case. I have x squared, the variable part, minus a constant. So that's right here. I haven't done this one yet. So my a this time is 1, and my b this time is 1. So they're both 1. So the substitution I'm going to be looking to make is I'm going to say x is equal to secant theta. If I take the derivative, I get dx is equal to, and the derivative of secant is secant theta, tangent theta, d theta. OK, so let's go ahead and begin. So this is different because I have a definite integral, so I will be plugging these bounds in at the very end. But that's the only difference, is one extra step at the very end. Let's plug in what I have here. So I'm going to do the integral of x squared is secant squared, and this is minus 1 over x is secant theta, and then dx is secant theta, tangent theta, d theta. So I've switched from being in x land here to theta land. So the bounds are different. I'm just going to leave them blank and keep it ambiguous. And then once I'm back in the original variable, I'll substitute it in. So I'm just going to leave these blank for now. I immediately see that these secants cancel. Also, this is an identity. I will stop writing these after a while, but just to start, I want you to see where everything's coming from. So tangent squared plus 1 is secant squared. So secant squared minus 1 is tangent squared. So I have the integral of the square root of tangent squared times tangent theta d theta. And there's nothing in the denominator now because I've canceled it. The square root of tangent squared will be tangent times another tangent, means I have tangent squared theta d theta. This I can handle very similarly to the last problem. So tangent squared, if you look at this again, this is secant squared theta minus 1. And then the integral of this is going to be tangent theta minus theta plus, well, not plus c, because I'm going to plug in a bound. So I'm going to do this for now. And I have two different things to plug in. But I'm not going to do that yet because I'm going to actually substitute back in now. So I need a triangle to figure out what this is. So let me go ahead and draw that over here. I'm given that secant is x over 1. Another way to write that is I could say cosine. So the flip of secant is this flipped over, which is 1 over x. I had x over 1, so cosine would be 1 over x. So cosine is adjacent over hypotenuse. And then if you solve for this remaining side here, you're going to see that it's x squared minus 1 under the square root. So now this is the situation. Tangent is going to be opposite over adjacent, which is just this. And then here I'm going to have minus theta. So if you solve up here for theta, you get cosine inverse of 1 over x is going to be equal to theta, if you use this very top equation that I wrote there. And now that I've substituted all the way back for x, I'm going to plug in my bounds here. I have 2 and 1. So to finish the problem, I need to evaluate this. If you plug in 2, you get 4 minus 1, this is root 3, minus cosine inverse of 1/2, minus, and then plug in, or put a parenthesis before the next part here, because you're going to subtract all of this. If you plug in 1, you get 0. And we get minus cosine inverse of 1. So this is going to be root 3. This is asking us which angle has 1/2 for the value of cosine. So let me write the actual question here. If you want to think backwards, what angle has to go there for that to be true? The answer is pi over 3. We're looking for an angle between 0 and pi for that answer. So the answer is pi over 3. Go to your unit circle for that. Minus, here I get 0. And then here's same question. Cosine of what angle gives me 1, and I have to be between 0 and pi? Well, 0 degrees is the answer for this. That's cosine is 1. So this is all just 0. So our final answer is going to be root 3 minus the pi over 3. OK, and that's it. So as you can see, very similar process for all of them. Just lots of pieces that go together. So make sure you practice a few of these, because in the next lesson, they're just going to get more difficult. There is a trigonometric substitution 2, where the things we're going to be dealing with will just be even more tricky.